That's what it is. So check it out. Watch. That tells me, let's go way back. Let's go back to this guy. What we have is, instead of being beholden, being absolutely strapped into this idea of a geometric context, where if it's not a if I can't finagle it into looking like a geometric series, I'm screwed. Not at all. What I now have the ability to write, which is so cool, and here it is. Here's the punchline to this sordid little tale. If I want f of x to equal an infinite Taylor series centered at A, remember this is c sub n times x minus a to the n, which can really be written as the sum, as n goes from 0 to infinity, of fn, the nth derivative of the function evaluated at a, divided by n factorial times x minus a to the n. Now, we're going to have a good time with this. Check this out. You're going to love this. This is fun. Let's do it. We're going to figure out what e to the x is. Let's keep it simple. That's K-I-S-S. Keep it simple, stupid. Let's center it at x equals 0. All right? Now, you know what? I'm going to have to do just a little erasing here because I want everybody to see what's going on here. I'm going to center it at 0. And I want to write in big, bold, let's go green, because it's the most obnoxious color, and there's no way this is going to get through. I know that c sub n is equal to the nth derivative of the function evaluated at a divided by n factorial. Right? That's c sub n. That's this guy. Whoa, that's this guy right here. In this case, I had myself a Maclaurin series because it's centered at 0, but don't worry about that. Okay, so what we're going to do is we're going to build this thing out. You know what? I'm going to run out of room. Let's back up. I'm sorry, you guys. Give me just a second. I don't want to be all mushed in. Okay, so we know that as a quick recap, I know that I can now rewrite any function that isn't already polynomial. This is the magic of a Taylor series. I can take any function that's not already a polynomial, and I can turn it into something that looks like a polynomial as long as I let n go to infinity. It's going to be one of these guys, which we know is polynomial, right? All power series are polynomial because these are just coefficients. They're just numbers. And then this is just x to the 0, x to the first, x to the second, x cubed, etc., etc. Think about how powerful that is for just a second. It's going to be n equals 0 to infinity. Remember, c sub n is the nth derivative evaluated at a over n factorial times x minus a to the n. This is the definition of a Taylor polynomial. Poly centered at a. Now, stand back. Here we go. We're going to find the Taylor poly for f of x equals e to the x. And let's do it for a equals 0. That just means it's Maclaurin. Maclaurin. I'm going to say that over and over again. Sorry, guys. Okay, so let's look at how this works. I already know it's centered at 0, right? So if I want to do e to the x equals, I'm going to have a sum as n goes from 0 to infinity of, I already know a is 0. So what I'm going to get is a term that says x to the n out here. But what I then need to do is figure out what these c sub n's are, and I'm going to look for a pattern. So it's always really simple when you start out. I know that c sub 0 equals f of 0, right? Because c sub 0 always equals f of a, and since a is 0, so I know that this is e to the 0, which is 1. Sweet, I've got the first term. But I need a pattern. I need to be able to figure out what's going on here. All right, so how did I do this again? Well, first thing I do is I find f prime of x. So f prime of x is equal to e to the x. Ooh, isn't that nice? So f prime at 0, remember f prime of a, how we did all this back here. F prime of a, f double prime of a, f triple prime of a, etc., etc. All right? I'm going to f primed at 0. Ooh, look at that. That's going to be 1 again. How nice. Isn't that cute? All right, sweet. Now wait, okay, so the formula is that. So really what I should be thinking about isn't so much that this is just 1, but it's almost as though this is the 0th derivative of e to the x, so it's just the value of the function itself, right, is equal to f of, the zero derivative at 0 is 1. We could think of this as divided by 0 factorial, couldn't we? Because 0 factorial is just 1. I could think of this as being the first derivative, right? So if I want to find c sub 1, I know that's going to be f primed at 0 divided by 1 factorial, which is 1 divided by 1 factorial, which is 1. All right? I'm just following this guy. I know it's tricky to play with, but you'll get used to it, I promise. We're going to need the second derivative, right? Because that's the nth derivative, and when n equals 2, I'm going to need that second derivative. Watch what happens. The second derivative, thank God, it's e to the x, right? So f double primed at 0 is e to the 0, or 1. So this implies that c sub 2 is equal to, you ready? It's 1 divided by 2 factorial. Look, I'm just following. So f triple primed of x is equal to what? What's f triple primed? It's e to the x again. And that implies that f triple, did I say triple? That should be a 3, shouldn't it? 3. And that should be a 3 there. Of at 0 is equal to 1, which implies that c sub 3 is equal to, well, what is it? C sub n always equals the nth derivative evaluated. We already got that part, so it's 1 divided by 3 factorial. So look at what's going on. I mean, are you starting to see the pattern? What's your guess that c sub 4 is going to be? Well, you're always going to get a 1 for the nth derivative at 0, right? So c sub 4 is just going to be 1 over 4 factorial. C sub 5 is going to be 1 over 5 factorial. C sub n is going to be 1 over n factorial, which implies that e to the x can be written as the sum, as n goes from 0 to infinity, of x to the n times 1 over n factorial, or the fancy way of doing that is x to the n over n factorial. Now, let's see what that polynomial is, and then let's graph them together and make sure that Ripley is not telling tales. All right, here we go. So I know, wow, what happened to my pen? I know the first term is going to be 1, right? C sub 0 is always going to be the first term. If the first term isn't C sub 0 in these guys, when you're just doing a basic Taylor polynomial, you need to pay attention to why that is. Okay, so anyway, so I know the first thing I'm going to, what's the next term going to be? Well, it's x to the 1 divided by 1 factorial, so that's just x. The next one's going to be x squared divided by 2 factorial, that's just x squared halves, plus x cubed divided by 3 factorial, which is, I'm going to actually put factorials here. Let's go 3 factorial. We'll tweak them a little bit when we plug it in our calculator. And then plus x to the 4th over 4 factorial. And then let's see, what's 4 factorial? We got 24th, all that good stuff. Let's do just a couple more terms. So plus x to the 5th over 5 factorial plus ... Now let's see. I'm going to graph both of these at exactly the same time over here. So let's toggle up. Toggle up. My goodness, what's going on here? I'm going to have an e to the x. So let's see, second e to the x. And cruise over. And then I am going to hit a standard window here, and we'll talk a little bit about radii and intervals of convergence. But just watch for a second. Make sure I'm not crazy. So 1 plus, I'm just going to plug all these guys in. Now, remember back when we were talking about functions as power series, if I wanted to, I could show you how these begin to fit themselves around e to the x, but let's make sure they start looking like it first. So this is going to be 1 plus, and then I got x squared halves plus x cubed, and then down, and I got to go, what, 6th divided by 6 plus, what am I doing? X to the 4th divided by what? 6 times 24, or 6 times 4 is 24, divided by 24, and then plus x to the 5th, x to the 5th, and we'll cruise over here and divide by what? 120, right? Just times 5, so 120. Let's see how close we get. All right, I may have to throw some extra ones in there. Remember, my window was tweaked from last time, so let's look at our window. Yeah, let's go to zoom standard, which is zoom 6, and we'll see what happens. So here comes e to the x, And here comes the other function. Now, look at that. That's crazy, huh? Now, let's zoom in just a touch. Let's see what happens. If I hit zoom 2 and I center it, let's enter and see what happens. So there's e to the x. And there's my other function. Look at it. Look at how close it is to e to the x. Now I'm going to go back to Zoom Standard because I know a lot of you guys are going, but Ripley, wait a sec. What happened to this crazy tail over here? What is that? So here comes your polynomial, right? This is a 6th degree. So this right here is extra because I've got myself a 5th degree polynomial. So I'm always going to have this error. This is how much I'm going to be off by. But think about it. If I add one more term, let's go down here, and I'm going to add, let's add one more term and see how close we get. Or let's go, yeah, let's add one more term because it starts getting hard to multiply these. So 6, sorry you guys, bear with me. And I'm going to add in, let's go, I'm going to add in, I think that's, let's see, sorry, this thing takes forever. So I'm going to go plus x to the 6th. Let's see how much more accurate we get. X to the 6th divided by, well, I get 6 times 120. Ooh, wait, screwed that up. Delete. X to the 6th, and then divided by 7, 120, or x to the 5th, what, 6 times 120 is, what, 720? So 720, right? And then graph it. Watch what happens. So here's e to the x. Now remember, this is going to be a 6th degree polynomial, so it's going to come down from up here. But look what's happening. I'm getting closer and closer and closer in the parts that match up. Now, if I let n get bigger and bigger and bigger, what happens is this tail, this error, and you may say, Rippy, that's quite a bit of an error, but you'll see where we use these down the road. Right now, we're just trying to get our brain around how these work. Let's say that I were to let n go to 20. What would happen is I'd end up with a 20th degree Taylor polynomial, right? And this tail would be way out here. It'd be off of the calculator. You wouldn't even be able to see it. It'd be gone. So for all intents and purposes, from -10 to 10, this curve and this polynomial are exactly the same within that frame. And here's the thing that I know is going to drive some of you guys crazy because you're always going to be, well, Ripley, this thing is either going to be flipping up this way or it's going to be flipping down this way depending on if the degree of my polynomial is odd or even. You're right. But as I let n go to infinity, what happens is that what you lose is that ability to have this thing flip back and forth. There's no part of the curve e to the x that isn't perfectly accounted for the polynomial. I know, it's crazy. We will play with the error and how to wrap our brain around that. This is just an introduction to how to come up with a Taylor polynomial so we can start talking about more interesting things. Okay? All right, so I just wanted to show you that. I always thought that was pretty cool. Let me give you one more. Let's just play with one more. Let's do, just to give you some practice.